Okay, so last class we did the independent electron pair approximation and showed that it was size consistent. And by size consistent, I mean that if you have two fragments of a molecule which are separated by a very large distance, that's say an infinite distance, then the energy of this supersystem or dimer should be a sum of the energies of the monomers or the subsystems. And this is called size consistency. And we showed that if if we take a dimer of two hydrogen molecules which are an infinite distance apart, so if they are an infinite distance apart, then this is indeed true for the independent electron pair approximation. So it is size consistent. The argument that we used was, of course, that the orbitals on these fragments, there are only two for our particular case because it's the minimal basis, so one occupied and one unoccupied orbital on each hydrogen molecule. And the argument was that since there is no overlap between these orbitals on fragment 1 and fragment 2, then any interaction between electron 1 on fragment 1 and any other electron on fragment 2, those interactions are all zero. So that was the argument which told us that certain two electron integrals which are involved in the pair correlation energy, they are zero, and this helps us to show that the correlation energy of the dimer, which is written as 2E correlation, was twice the energy of each monomer, which is basically a statement of the size consistency of the theory. Now, then at the end of the class, I also mentioned that the fact that the orbitals are localized on each fragment, that is not a necessity, because you can always rotate the orbitals and make them delocalized while keeping the Hartree-Fock function, its energy and all its properties the same. So the orbital set is not unique. So it remains to be seen if the size consistency of IEA is true for any set of such orbitals. And this property is called invariance under orbital rotation, which can be equivalently called invariance under unitary transformation of orbitals. Okay, and we will start there today. So remember that the canonical Hartree-Fock orbitals are unique for non-degenerate orbital energies. So if I say that I want the canonical solution to my Hartree-Fock equations, I get only one set of orbitals for the non-degenerate ones. But if you have degenerate pairs, then you can rotate them among themselves, and some linear combination of original orbitals will give you the same energy for that set of degenerate orbitals. Okay. And this flexibility can cause problems for correlation theory. So let's start there today. So today is lecture 34, and we will talk about invariance of IECA under orbital rotation. And here we are particularly talking about degenerate orbitals. Again, we will take our very familiar example of two hydrogen molecules separated by an infinite distance. Okay, so we will take a hydrogen dimer. So this is a non-interacting system. And now instead of taking orbitals which are localized on each fragment, we will take some particular linear combinations, which are basically the ones which are maximum possible delocalized. So A and B, remember, are my occupied orbitals, and I am taking a linear combination of the localized occupied orbitals, which remember we wrote as 1, 1, where 1 means the lowest energy level, so the lowest energy orbital, and the subscript is the fragment number. So this is 1, 1 plus 1, 2. So orbital on fragment 1 plus orbital on fragment 2. This is of Gerardet symmetry, spatial symmetry. Then we take the second occupied orbital, which is 1, 1 minus 1, 2. So this is the antisymmetric combination of the occupied orbitals of fragment 1 and fragment 2. And this is Gerardet symmetry. Next we have the unoccupied ones. So R is 1 by root 2, 2, 1 minus 2, 2. Now the 2 orbital itself was Gerardet symmetry, so an antisymmetric combination is Gerardet symmetry. And then you have the other unoccupied orbital, which is a symmetric combination of the Gerardet orbitals. So this is Gerardet. And let me just write down that these are the occupied and these are the unoccupied. Now A, B, R and S are now not on any particular fragment. They are delocalized over the full molecule. However, the Hartree-Fock determinant is the same and they are still orthogonal. Okay. So what is the Hartree-Fock determinant now? The Hartree-Fock determinant now is AA bar, BB bar, and this is equivalent to what was before 1, 1, 1, 1 bar, 1, 2, 1, 2 bar. Okay, and these are all 4 by 4 determinants because this is a 4 electron system. Okay, now how can you show that this that the determinant remains the same with this new orbitals? So the Hartree-Fock determinant remains the same. So now you have to think about it a little bit. So when you have a determinant, then if I replace, so I have a determinant, I have chi 1, chi 2. Okay, let me just do a 2 by 2, and then it will take a little time. I have chi 1, 1, chi 1, 2, chi 2, 1, chi 2, 2. Okay, so this is my, let's say, the Hartree-Fock determinant. Now, if I replace chi 1 with the linear combination of CK, chi K 1, also this one, sorry. Then, by the property of determinants, you can take out the sum over k chi k as a factor. And similarly, if you do the same for chi 2, if you put Cl chi L, oh sorry, this will be a CK square because by the property of determinants. Sorry. So then you will now have also take out the sum L Cl. So then you have sum KL CK square Cl square with the original with chi k1, chi k2, chi l1, chi l2. Now, what is the value of this for our case? So, for our case, this is basically 1 by root 2 square plus 1 by root 2 square into 1 by root 2 square plus minus 1 by root 2 square. So these are the coefficients of 1, 1 and 1, 2 in A and B. Sorry. And this is equal to 1 into 1, which is 1. So basically you get back the same determinant.
Ma'am,
Yeah.
how did you get the CK square term?
Uh,
You take common from the upper row, right?
yes.
That should be CK.
No, actually there is a sum. So I have to, I didn't open it out. So if there is a sum, then every, so it will be CK chi1 plus again, let's say C1 chi1 plus C2 chi1 and then again C3 chi1. So it's a whole series. So this will become a big sum of determinants. And you will have CK of such terms. Each determinant you can take CK common. So over here there are many steps. So you have to open them out. Okay, C1 chi1, C1 plus C2 chi2 plus C3 chi3, and again C1 chi1 plus C2 chi2 plus C3 chi3. Okay, and then you have to write them out as now a sum of the determinants. And then if you take C1 common from all the determinants which have C1, so C1 chi1 will come. So you will have a C1 common here in one determinant, and you will have that many such terms. So you will have C1 into C1 as one factor. And then when you take C2 common from the other set of sums, you will have C2 of such determinants where C2 has been taken common. So if you open it out, you'll be able to see it. I'll have to write a lot, so I was lazy and I didn't write it. So if you want me, I can try to do it. So let's see. Let me write in a different color then. So I will have a C1 chi1 plus C2 chi2. C1 chi1 plus C2 chi2. This is not working out like this. I don't think I can write this out explicitly. Sorry, just 1 minute. Okay, so let me write write it out algebraically instead of in the determinant form. Easier. So that was chi1 1, chi2 1, minus so, sorry. This is so I have 1 by root 2 from 4 terms, and I have A, which is 1 1 plus 1 2. Then I have A bar, which is 1 1 bar plus 1 2 bar. Then I have B, which is 1 1 minus 1 2. And I have B bar, which is 1 1 bar minus 1 2 bar. So this is one electron in each orbital. And because this is a determinant, you will also have the other term for electron 2. But just working out one term will be enough, because the other one will work out in the same way. So you will have, so this is also, sorry, so this is the full determinant. It includes the negative term, but I can also evaluate just one product, then that is enough. And that is then 1/4. And I can take 1 1 common. Then I have 1 1 bar plus 1 2 bar. Into 1 1 bar minus 2 bar. Then I have plus 1 2 common, 1 1 bar plus 1 2 bar with the 1. So I'm changing the sign on this one. 1 2 bar minus 1 bar. Am I missing something? 1, 1. Oh, sorry. One more. Right, so I've only opened this out over here. Then I can open it even further. That is 1 bar. So it's the easiest way to do this without opening everything up. Let's see. I guess we just have to open everything up. I can't find an easy way of doing this. So, okay. So, 1, 1 into so let me take 1, 2 out of this. Minus 1, 2. So we can exclude the terms which have 2 1 1s or 2 1 2s because those determinants will be 0. They will cancel with the counter term, with the minus term. So a term like 1 1 1 1, that I am not writing. So I'm only writing the ones with unique orbitals. So it's 1 1 1 2. This one. Then I have 1 2 here, so I can take the 1 1 from here. So this will also become a plus in the determinant form. It's best to, I think, then keep the determinant notation. Okay, keep the determinant notation. So which means I'm keeping both terms because I have to also keep track of which order the orbitals appear. Because if I swap the orbitals, the sign of the determinant will change, and that is important for me. So I will keep the determinant sign. And then it also becomes more correct for me to remove terms which have 2 repeated orbitals. So you have 1 4, then 1 1. Okay, let's follow the order. 1 1 1 1 bar. That is a that is fine, and that is multiplied with both these terms. So this and this, 1 1 bar minus 1 2 bar, and then I have 1 1 minus 1 2. That is one determinant. Then with 1 1 1 2 bar, 2 bar, and 1 1 bar minus 1 2 bar, 1 1 minus 2. That is the other one. Then comes this one. So 1 2 1 1 bar, 1 1 bar minus 1 2 bar, 1 1 minus 1 2. 1 2 1 2 bar, 1 1 bar minus 1 minus 1 2. Sign. So this is 1/4. Okay. Then 1 1 bar. So this term is repeated. That goes away. So 1 1 bar. You have a minus sign. 1 2 bar. 1 1 minus 1 2. Plus 1 1 2 bar. So which one am I doing? This one. 1 2 bar, 1 1 bar, that is fine. Minus 1 2 plus again 1 1 1 1. What happened? My pen is not writing anymore. 1 minute. Sorry, my pen stopped working. Just 1 minute. Yes, I need to charge it. What happened? Huh? Strange. Oh, okay, okay. My pencil is. Okay, that my finger also works. This is 1 1 1 2 bar, 1 1 bar. Then that is not there. Then I have 1 1 1 1 1 1 2 bar. So I'm writing with my finger, so it would be even more untidy. So there is a minus sign here. So you see, that's why I was avoiding having to write all this. 1 2 bar. Then it's this one. Then that is a 1 2 bar repeated, so that's plus 1 2 1 1 bar 1 with the minus sign. So this is 1, 2 bar. And then 1, 1 minus 1, 2. Okay. And then from the last term, I have 1, 2, 1, 2 bar. And 1, 1 bar. 1, 1 minus 1, 2. Okay. So this is why is no, my pencil is still not working. Okay. So this was 1, 1, I guess. So then that is not there. Minus, minus, plus. 1, 1, 1, 1 bar. 1, 2 bar. 1, 2. Okay. That is 1 term. Then from the next one also, I will only have the minus term, which is 1, 1, 1, 2 bar, 1 bar, 1, 2. Then I have minus only the first term, so 1, 2, 1, 1 bar, 1, 2 bar, 1, 1. And from the last term now, I have again minus 1, 2, 1, 2 bar, 1, 1 bar. No, this is plus term, plus 1, 1. Okay, so we have to look at getting everything in the same order. So this will develop a minus sign, I guess, I2 bar. 1, 1 bar. So this will be a minus something. Then the second term will be minus, minus, plus. So that will remain a minus. Then the third term will be I2. So, okay, I1 bar. So this is 1 change and 2 change. So that is also a minus sign. And then 1, 1 bar. So the last one is also a minus sign. So somehow we have an overall mistake of a minus sign. This should have been plus 1. So what we got is 1/4 into minus 4 equal to minus 1. Minus 4, which is minus 1. But we must have made an overall sign mistake somewhere. Anyway, what with all the messy algebra, I must have made a sign mistake. But this is how you work it out. Maybe if you do it calmly sitting at home, you will get the right answer. So this should have been 1/4 into 4, and that will give you a 1, which will indicate that the two determinants A bar, B bar, and 1, 1, 1, 1 bar, 1, 2, 1, 2 bar, those two are the same. So I will since this is so untidy, I'll also do it nicely before I put up the notes on VLearn. So hopefully you will have the correct one soon. I'm not wasting any more time working this out. It's just a lot of keeping track of signs and indices. But now I don't know what to do because my Apple Pencil doesn't seem to work. What happened? Just give me 2 minutes to try and fix my pencil. Otherwise, I can't write. So that is not a good thing. Okay, it's connected. Good. I'm just disconnecting the call and I'm fixing my Apple Pencil and I'll come back in 5 minutes, okay? So you can stop the recording for this class as well. And then we'll start again.